Hello, this video is for the class Math 1324 and it will cover section 6.4 basic matrix operations, examples 5 through 9 from the textbook. For example 5, we are going to add some matrices, but before we do that, let's go ahead and read the problem and see what each row represents and each column. So we have a drug company and is testing 200 patients. So that will be the total, and that could always be a question on your homework. To see if paying off a new headache medicine is effective. Half the patients received the medicine, paying off, and have received a placebo, which it will be just a sugar pill, for example. And out of those, they were 50 patients tested at the same time. So I know the total says 200, so the first trial includes 50 patients, and then the next three trials include 50, 50, 50, so that's how we get 200. So just to go over the columns, well, let's go over the row first. So the first row, R1, it represents the patients who took the medication. And so the total of those patients, you can see here, 22 plus 3 is 25. Now, R2 represents the patients who took the placebo, and we get 8 plus 17, that is also 25. So those 25 plus 25 will give you the total of one trial, which is 50. Now, if we look at the columns, so now vertically, out of the patients who took the pain off medication, 22 reported yes to have obtained pain relief. And out of the patients who took the placebo, 8 of them reported yes, that they had obtained pain relief. If we look at the second column, 3 of the patients who took the medicine reported no pain relief, and 17 who took the placebo reported no pain relief. So this matrix is showing us how to organize the data. So now for the next 3 trials, every time we look at the matrix horizontally, we're talking about the patients who took the medication, which they're calling pain off. And the second row represents the patients who took the placebo. So every single matrix will have for the first column, the patients who responded yes to have obtained pain relief, and the second column will be the patients who reported no to have obtained pain relief. So we could do that for each matrix. Now, this will be an application of matrix addition. And to answer the question, which is the total, what will be the total results of the test, you will obtain that by adding the 4 matrices. So this will be the first trial, second trial, third, and fourth, and this will be the total. So because matrix addition is defined as you add the elements that have the same location in the matrix, such as the ones that I'm circling, they're all located in the first row, first column. So if you add all of those, you obtain 85. Now we go to the first row, second column, 3 plus 4 plus 6 plus 2, we will obtain 15. Now I'm going to move on to the first column. So 8 plus 6 plus 10 plus 3 will give me 27. And finally, the second row, second column, 17 plus 19 plus 15 plus 22 will give me 73. And that is the end of the problem. So if we look at the matrix that represents the total, and we were asked a question such as, out of the patients who took the pain relief medication, how many of those reported to have obtained pain relief? And the answer for that will be here, 85, because that is located in the first row, first column. If the question was out of the patients who took the placebo, how many of those reported that they did not obtain any pain relief? And the answer for no will be in the second column, second row for placebo, 73. Remember the total is 200, but out of those 200, 100 were given the medication and 100 were given the placebo. And so that is the end of this problem. Let's move on to the next one. And for example 6, we have this matrix subtraction, and just recall that addition, subtraction, they are the same thing. And subtraction is addition, but just of negative numbers. One thing we can do here is distribute this negative sign, like if it was a -1 outside parentheses, for example. And so because of that, the negative sign gets distributed to every single entry or element inside the matrix. Remember, the elements are the numbers. And if I wanted to rewrite this matrix or this subtraction, it will be the matrix 1, 2, 3, 0, -1, 5. And then I could say, if I was to distribute the -1, I could just say plus, and then by distributing -1 times -2, it would give me +2. -1 times 3 will be -3. -1 times 0 is 0. -1 times 1 is -1. -1 times -7 is +7. And -1 times 2 is -2. So to answer this question, remember you have to add the numbers that share the same location in the matrix, such as the ones that I'm circling. So now here we're adding because we are distributed the negative sign. However, you could just do this. You could tell yourself what would be 1 minus -2. So that is the same as saying 1 plus 2. And that will give us 3. Then if we calculate 2 plus -3, that would be -1. 3 plus 0 is still 3. 0 plus -1 is -1. -1 plus 7 is 6. 5 minus 2 is 3. And here I'm just adding because I already distributed the negative sign. However, that is not necessary. The next one I will do without distributing the negative. So in this case, we have two matrices, and also they have to have the same dimensions. So we have here a matrix that has 1 row and 3 columns. Again, here 1 row and 3 columns, and by the way, we call those row matrices. And to calculate the difference of those two, I could say 8 minus 3, that would be 5. Then 6 minus 5 will be 1. And finally, -4 minus -8. So that would be something like -4 minus -8, which will be -4 plus 8, and that goes to +4. Now, the next one, the subtraction here is, actually, we shouldn't say equal. We just say is undefined. And for the purpose of your homework on my math lab, I'm not sure if what word they will give you, but it could be something around it's not defined, it's impossible, undefined, something around that. The reason is that the second matrix, the dimensions for the second matrix are 2 by 1. And so because we do not have the same number of rows and columns, we cannot subtract the numbers. Okay, so here is a summary of how you will do a difference of two matrices. So they must have the same dimensions. And you take the difference of each corresponding element, so the ones that will have the same location in the matrix. So we're on to the next problem, and this is called scalar multiplication. It is something as easy as distributing an integer. For example, if you have -3 times, let's say, x plus y, This will be negative 3 times x, negative 3x, and then negative 3y. It will be negative 3y. You could also do this with numbers. So let's say you have something like that. So negative 3 times 1 will be negative 3. And then negative 3 times x will be negative 3x. So a scalar multiplication, well, first of all, scalar is just a number, a constant. And when we do that, we're going to distribute the number to every single element inside the matrix. So we will start with negative 3 times 2, that is negative 6. Negative 3 times negative 5 is positive 15. Then negative 3 times 1, negative 3. Negative 3 times 7 is negative 21. And then we do the same thing with the last two numbers from the third row. Negative 3 times 4 is negative 12, and negative 3 times negative 6 is positive 18. Yeah, so that's all it is for scalar multiplication. And if we were to have something such as negative and then a matrix, let's say 4, 1, 0, 2, or negative 2. What this means is that you will have a negative 1 in front of it, and that will be the number that you distribute, which is the concept of subtracting two matrices. So in this case, we will have negative 4. Negative 1 times 0 will still be 0, and then negative 1 times positive 1 here will be negative 1. Negative 1 times negative 2 will be positive 2. And so what we will say here, if let's say that matrix A was the one that I wrote first, the one that we obtained by multiplying the matrix by the constant negative 1 is going to be called the additive inverse of matrix A. So in summary, it will be the same numbers but with opposite signs. So we call that additive inverse, just like we have additive inverse for real numbers. For example, 2, if you want to add a number that will give you 0, you already know it is a negative 2. And so we call that an additive inverse. In fact, 2 and negative 2 are additive inverses of each other. So matrices do have that same characteristic. For that, every single element or number inside the matrix will have the opposite sign, or it will be a negative 1 will be distributed there. And so we have the same thing written here. And so that will be for additive inverse. In the next section, we are going to cover multiplicative inverse, which will be what we use instead of division. Division with matrices does not exist. Okay, so here the question is find negative A, or the additive inverse of A, of this one, and find negative B, or the additive inverse of B. And the answer is already here. So as you can see, every single sign was changed from positive 1 to negative 1, from positive 2 to negative 2, positive 3 to negative 3, 0 still 0, negative 1 changed to positive 1, and 5 changed to negative 5. The same thing happened with matrix B. Every single entry changed to its opposite sign, just like if we were distributing a negative 1. So negative 2 changed to positive 2, 3 to negative 3, 0 to 0, 1 to negative 1, negative 7 to 7, and 2 to negative 2. Now, if we were to add a matrix plus its inverse, we will obtain what we call the zero matrix. And it will be a matrix with zeros everywhere. So right here I'm writing, following the example that we have here for matrix A, which is a 2-row by 3-column. The additive inverse of A happens to be the same. It must be the same, actually. And so if we were to add A plus negative A, we will obtain all zeros, and we call that the zero matrix. By the way, that is also called the additive identity. And just to remind you, with numbers, just like I gave you the example of 2 plus negative 2 will equal 0. We do call this two additive inverse. They are the additive inverse of each other. And we do call 0 the additive identity. In the next section, 6.5, we are going to cover the multiplicative identity of matrices. And that one will be a matrix that if you multiply it by another matrix, you will obtain the same matrix that you started with. Just like if you had a number and you will multiply it by a number to give you the same number. And I guess you could all know or guess that the number will be 1. So just like we have a multiplicative identity for real numbers, we will have a multiplicative identity for matrices. With numbers, we have also covered this concept. What would you have to multiply 5 to give you a 1? And that would be 1 over 5, because we multiply straight across, and this will equal to 5 over 5, which equals to 1. So just like we have multiplicative inverses with real numbers, we also have multiplicative inverses with matrices, and that's the symbol we will use, but I don't want to spoil the surprise you, so I will teach you that when we see each other in class again. The last slide is it has a summary of the properties for addition of matrices, and when we say addition, we're already including subtraction. So addition with matrices is commutative, meaning that you can change the order and you will obtain the same. It is associative, meaning that you can group 2 matrices. If in the event that you were adding 3 or more matrices, you could add 2 at a time and then the third one, such as B plus C and then add A, or you could start by adding A plus B and then add C. Then we also have the identity property of addition. So that is when we use the additive inverse, which is the 0 matrix with zeros everywhere, and that will result in the same matrix. And of course, it is also commutative. Inverse properties, we went over about what is the additive inverse of a matrix. So it will be the same matrix, same numbers, but each element with its opposite sign. And if we add a matrix plus its inverse, we will obtain the 0 matrix. And of course, that is also commutative. And that's it. This concludes the video for section 6.4. Thank you for watching. Make sure you take notes and do your homework.